Good evening, everyone. Myself, Gautam Sharma. I welcome you all in a Sapience Education. Today, we'll go discuss about electrostatic potential and capacitance. This is part 2 video, and some of the topics have been taught in the part 1 video, so you can also go through there. So it is a regular video, so you will get regular videos and not at a regular interval time. So being up for update, you must subscribe our channel so that you will get regular updates for the class 12 board as per the latest syllabus. So now let us try to start my class. Here we go. What is the topic we should go? So first of all, electric potential at a point due to electric dipole. So what do you mean by electric dipole? We have already discussed in the previous sections that the electric dipole is, let us consider there is a positive charge, there is a negative charge, right? And the distance between is these two charges is 2a. So this is this system, whole system as a whole system is electric dipole. This is a dipole, right? Dipole means time is 2, pole means polarity. Okay. Now, if you are thinking that what is the dipole moment direction, when dipole moment, the formula P is equal to a q, and the direction will be always from negative to positive. This is the direction of, right? I hope you have understood now. Now let us try to find what the question is asking, that electric potential at a point into the dipole. Okay, see, you need to find a electric dipole at a point. Let us consider this is the point, and at this point you want to find electric potential due to this, right? So we know that the formula for electric potential is equal to 1 by 4 pi epsilon naught into charge by r, right? Here we have to both charge. Due to both charge, what will happen? Total net potential will be charge potential due to plus charge plus potential due to minus. Have to use this that we will get the net potential at a point P. Okay, so this is the topic, and we will discuss this here. Here, first of all, try to understand the diagram that electric potential at a point due to the electric dipole. So first of all, try to understand the diagram. This is a charge, this is positive charge, and this is negative charge, and the distance between this is 2a. See here, this length and this length is 2a. Well, distance length between these two charge is 2a. It means the dipole length is 2a. Okay, and I want to know the potential at a point, right? So how you will find? So first of all, we have to find potential due to charge plus q charge and minus q charge, and after that we need to add on. But the thing is that what is the distance between this charge and this charge? Okay, so we need to do this, right? Now let us consider, if you want to find the potential at a point P due to dipole. So from where we use the direction, where we use the distance from the dipole. Distance, if you want to take distance from dipole, you don't take any distance from any of the charge. You have to take from the center of the charge, because we are talking about the distance of the dipole. So let us in question they may ask you like this, that there is a electric dipole, positive and negative, and this is the dipole, and we want to find a potential at a point P, which is at a distance of r from dipole. So what will be your answer? From where you are taking an r, either plus q or minus q. So the answer will be absolutely wrong if you will take a distance from plus q or minus q. So you have to take a distance from center only, right? So here we will discuss same thing. Okay, here we will discuss same thing. So try to understand here. This is the dipole having a positive and negative charge, and the direction of the dipole is always, remember, from negative to positive charge, and the center of the dipole is this point O, and this is the distance r. Hence we have r is the distance of a point from dipole, right? So if r is the distance, now see here, can we make a line which is at a distance of r1 and another line which is distance of r2 from plus q charge and minus q charge respectively? From plus charge it is r1, and from minus charge it is your minus charge, it is r2. Now the thing is that both the distance are different. Now what we need to do, see here, very important, we have to find this r1 and we have to find this r2, and after that we will get the potential due to plus q charge and potential due to minus q charge. And if we get this both potentials, so what you will do, we have to add on. So before finding a potential, we have to find the distance, that is r1. Okay, so this is a very important thing, that how you will find a r1. Okay, so if your target is to find r1, how you will find r1? So can we take any distance perpendicular to this line? See here, I am taking a perpendicular distance like this, right? So this is the line which has been drawn by me or you. It may be anyone, okay? Now can you see here that this is forming an angle, triangle, right? So if you see the triangle and the angle is how much, theta? What is theta? Theta is the angle made by the distance, this distance, that is r, from the dipole. So let us consider, if you go back side and if there is a distance, see here, what is the angle made by this dipole? 90 degree. Now if I will take a point P, if I will take a point P at this point, so what is the angle between these two? See here, we can absolutely say that this angle is theta. So the same thing we are discussing here, the angle is theta, right? Angle is theta. Angle is theta. Now the angle is theta. This angle is theta, and this distance is a because it is midpoint and total distance is 2a. So this distance will be a only, and this distance we don't know. How you will find this? So can you tell that this is a cos theta? I won't explain why this a cos theta is coming, right? Now another thing is that there's another a, and this is angle again theta. So what will be this distance? A cos theta. Now see here, try to understand, this r1 distance is equal to this distance, yes or no? So the total distance from this is r, and this distance is a cos theta. So this distance and this distance both will be equal. So can we tell that r1 is equal to r minus a cos theta, because total distance was r, and this portion I will subtract. So we will get this distance r1. So finally you have got the value of r1, right? Again, I'm explaining you. See, the total distance from this is r. This distance is a cos theta. So what will be this distance? So definitely you have to subtract to r. Um, you have to subtract a cos theta from r. So finally, this length and this length both are equal. So we can directly write here. We can directly write here r1 is equal to r1 is equal to r1 is equal to r minus a cos theta. Now the turn is find challenge is to find a r2. See, if you able to find this distance, then you can easily find by just putting formula. Now the real challenge is that how to find a r2. See here, that is very important. R2, we want R2, right? We want R2. Now you know that this length and this length is same. So we can directly tell that this length is your R. So the R2 can be written as this distance plus this distance, and this distance you have got a cos theta. So R2 can be written as R plus a cos theta. So you have got this equation without any tension. So I hope you have understood now. right? Now our turn is to find a potential. Now our turn is to find a potential, right? So what is the formula for the potential? So the formula for the E is equal to 1 by 4 pi epsilon naught charge due to which we want the potential and the distance at which we want the potential. That is, so this formula we will use. Now the total potential at a point P is how much? So the total potential at a point P is equal to potential due to charge plus Q, that is this charge, see here, charge, and the potential due to Q. So we will use the general formula, same formula. So potential due to plus charge is equal to 1 by 4 pi epsilon naught into charge Q divided by R1 minus. Why I'm putting minus? Because it is a negative charge, so we have to put a minus, negative. So this will be again 1 by 4 pi epsilon naught into Q by R2. This is the R2. Now put the value of R1 as well as R2. R1 is equal to R minus a cos theta and R2 is equal to R plus a cos theta. So when we put this value to this one, so what we will get? We may get, let us discuss here. See here, as you have seen, again you just see the equation. This equation, finally the potential at a point P is equal to Q by 4 pi epsilon naught into 1 by R1 minus 1 by R2. Now let us go for, so R1 minus R2. So the R1 is equal to R minus a cos theta and R2 is equal to R plus a cos theta. Now I won't teach that how you get this. So this is a very simple calculation, basic maths. You can go here, cross multiply, and you will get this. Here, LCM, if you will take R minus a cos theta multiplied by R plus a cos theta, so a plus b, a minus b. So it will be definitely R square minus a square cos square theta, right? Now finally, our net equation become q into a cos theta into 4 pi epsilon naught to R square minus a square cos theta. Now the thing is that we were finding a potential due to dipole. So dipole means what? This P, which is equal to 2 into A into Q. Now you have seen that 2A into Q is here. So can we write here P cos theta by 4 pi epsilon naught into R square minus A square cos square theta. So this is the total net potential, right? Net potential at a point P we have got, right? Now, now the thing is that if R is very, very greater than this, so suppose this is a dipole and we want a potential at a point P. So R, definitely this R is very much larger than this A, right? This A. So if R is larger than A, so R A square can be neglected, and so A square cos square theta can be written as 0. So if you put here 0, so what we will be get? We will get potential at a P is equal to P cos theta by 4 pi epsilon naught R square. So this is what we want, right? So I hope you have understood this. So how to find a potential? So potential due to dipole is equal to the dipole moment in cos theta by 4 pi epsilon naught to R square. But you are wondering that why I have not put here that direction or a vector symbol. See, since it is your vector scalar quantity, potential is your scalar quantity. It is your scalar quantity. So is it is your scalar quantity, so uh, we have not put any direction. So I hope you have understood this, that potential at a point P due to dipole is equal to P cos theta by 4 pi epsilon naught into R square. Okay. Now let us go for potential due to dipole in an axial plane and equatorial plane. See here, what do you mean by x axial plane? See, the condition is that this is a dipole plus Q and this is a minus Q. We want a potential, we want a potential, we want a potential at this line only, that is axial line, axis of the line joining plus q and minus q. This is axial point, right? So if this was the point, so you are getting the angle theta. But when this will be that point, so your theta will be become 0, or theta may become pi. So if theta is equal to 0 or pi, so you are getting a potential. So potential will be how much? See, earlier we have derived that the potential P is equal to P into cos theta by P cos theta by 4 pi epsilon naught into R square. Now cos 0 theta is equal to 0 or theta is equal to 0 or pi. So you are getting either the value of a cos is equal to 1 or minus 1. So your final potential will be minus P by 4 pi epsilon naught into R square, or potential is equal to plus P by 4 pi epsilon naught R square. But we won't take this negative sign. So just we can directly tell here that the potential at a point due to dipole in an axial plane is equal to P dot R cap by, no need to write even R cap also, but if you want to find it, you can write here R cap by 4 pi epsilon naught into R square. Why I am using here R cap? I R cap. See, it is useless to use here R cap. No need because it is a scalar quantity. Now let us discuss about at an equatorial position. Now, what is equatorial position? Let us write here equatorial position. So the equatorial position is what? This is the charge plus Q. This is charge minus Q, and the line joining between them is this. And the equatorial plane is this plane. So at this plane, the angle will always be 90 degree from this. So if angle is 90 degrees, so what will happen? So the potential is equal to P into cos 90 divided by 4 pi epsilon naught into R square. So cos 90 is equal to 0. It is a 0, so net potential is equal to 0. So hence our conclusion is that the potential at equatorial plane position from dipole is 0. This is the point we have got it. Okay. Now let us go for a next topic. Now the topic here is potential energy of a dipole in an external field. Yes. What do you mean by this? See here. Basically, let us consider there is an electric field lines. Let us consider there is an electric field lines like this. Electric field lines like this, and it is your uniform electric field, right? It is a uniform electric field. Okay. Now, if you put a dipole in this electric field, so what will happen? So let us consider this is a charge plus Q, and this is a charge minus Q, and this is your dipole. Okay? The length between this dipole is 2a. Now what will happen? Basic things you have to understand. Basically, basic things you have to understand. Suppose this is a positive charge, so the electric field is going outward, right? This is the direction of electric. Now, if you place a positive charge, so what will happen? The force of at repulsion will be in this direction. So what is the conclusion? That the positive charge the force will act on a positive charge in the direction of electric field. Now if I will put negative charge, if I will put negative charge here, so what will be the impact? So the negative charge means what? There will be an attraction. So when there will be an attraction, so force due to charge, which is minus Q, will be in this direction. So the negative charge, the force acting is in against the electric field. Now I hope you have understood. Now let us go one by one. Here, since this is your positive charge, so let us consider the direction of electric field is in this direction, right? This is the direction of electric field. Now, if this is the direction of the electric field, then what will happen? What will happen to this charge? So the force will be acting upon this. So this is equal to F is equal to QE. Why F is equal to QE? Because we have already derived electric field is equal to force per unit charge. So from here we can get force is equal to QE. Okay. And here also the force is equal to QE. F is equal to QE, but in opposite direction. See in dipole the charges are equal. In dipole magnitude of charge is equal. Magnitude of charge are equal. So if magnitude of a charge are equal, then what will happen? So force F is equal to QE. One is in this direction, another is in this direction. So the thing is that when you have studied mechanics in the class 11, so what you have done? See, let us consider the force is acting downward here is equal to E, and the force is acting on a down upwards. This is also equal to QE. So net force is equal to what? Net force is equal to 0. So net force acting on the dipole is 0. But what will happen? What will happen to this dipole? There is a distance or gap. So whenever you have seen a gap, so what will happen? Automatic torque will be there. So you have seen any bicycle, if you have applied a force in this opposite direction, so total force will be 0, but it will create a torque, it will create a rotational thing, and we need to find a torque, right? So what is the formula for a torque? Torque is equal to force into perpendicular distance r. Now we will discuss this in a proper way. So I hope you have understood the terms and how to do this. See here. Now I have already explained you. In spite again and again, I am explaining you this thing. See, this is the electric field direction, and there is a positive charge, and the force is QE, and either in this direction, the force is in the opposite direction acting, which is equal to QE. And the dipole moment direction is from negative charge to positive charge, right? Now, work done in rotating an electric field is equal to how much? Tell me. Work done in rotating an electric field dipole by d theta. For example, if you have, see here, if you want to, see here, if you have rotated this dipole to this direction, so you have moved by d theta. While rotating, you have to apply a force. You have to apply a torque. And when you apply a torque, so you are doing a work against the torque. Why? Because see here, this force and this force tends to move this dipole in this direction, but you are applying a force which is just opposite direction. You are applying a torque to rotate against it. So here what we are doing, so work done in rotating an electric field dipole by d theta in an electric field is equal to dw. dw is equal to torque into d theta. Why? Because work done is equal to torque into d theta. See here, you have you know these things that work done is equal to force into displacement, right? But here in place of rotation, the work done will be in force of force. Here torque is responsible. In force of normal displacement, theta is responsible. So here we have to write dw, that is work done, is equal to external torque into d theta. Now total work done in rotating from theta 1 to theta 2. Earlier, let us consider, earlier the dipole was like this, which is an angle of theta 1. Now we have moved for theta 2. Now we have moved the dipole in such a way that the angle become theta 2. Now we need to integrate so that total work that will be done. Work done will be, we will get the work done. So when we integrate it, so theta 1 to theta 2, so what we are getting? External torque into d theta, and that is from theta 1 to theta 2, right? So if it is from theta 1 to theta 2, so what will happen? See, what will happen? See, try to understand again. See, work done is equal to what? Work done is equal to torque. Let us consider a small work done is equal to torque into d theta. Why? Because earlier the electric field, this was electric field and this is theta, or this has been moved. This is theta, and now let us consider we have moved this dipole, that is positive, negative charge and positive charge. We have moved this dipole this position. So when we move this, so we have to apply an external torque, torque external, and which is equal to tau into d, tau external. Now work done will be equal to tau into d theta, right? And when we move, when we move any dipole from the position theta 1 to theta 2, then what will be the work done? So we need to integrate from theta 1 to theta 2. And if you will integrate this, then what you will get? You will get the total work done. And total work done is equal to tau into d theta from theta 1 to theta 2. Theta 2. So tau into d theta, theta 2 minus theta 1, right? So here uh, we can then put here how you will find out work done. Now in place of torque, what we can write? Torque we have already find out in previous classes. Torque is equal to PE sin theta. P is the dipole moment, is the electric field, and sin theta. Now if you put the work value of a torque in this, so what you will get? PE sin theta from theta 1 to theta 2 into d theta. So we need to integrate this. So basically you know the integration. So P is constant, electric field is constant, so we have it has come out, and the integration of sin theta will become cos theta, and our value or our initial condition and final condition is theta 1. Now when we do this, then we have to put here the values. So let us consider cos theta 2 minus cos theta 1 and minus P. We can also rearrange the equation as, no need to rearrange, we can directly took here, change, see here, this is the condition. So why I have put here delta U? See, ultimately what you are doing, you are applying an external force or external torque, sorry, see here, we have already, we have applied an external torque, so we are applying an energy. So our work, whatever work we have done, this has been converted into a potential energy. Why? Because it will change its position such that it will store some of the energy. When you apply a force, so it will get stored in energy, and when you remove your force, a torque, so what will happen? It will again come to its original position. So here, change in potential energy is equal to, that is U2 minus U1 is equal to work done, and this is equal to minus P cos theta 2 plus cos theta 1. Finally, potential energy, potential energy. What was the topic? Potential energy of a dipole in an external field. Potential energy of a dipole in external external electric field, electric field will be equal to P cos theta 2 minus theta 1. So I hope you have understood this concept. So here we go. It's very important again. Note, electrostatic potential energy of a dipole in a uniform electric field is defined as work done in rotating a dipole from a direction perpendicular to the field to the given direction. Why it is taken as a reference point as a 90 degree? See, when there is an electric field like this and there is a dipole like this, there is a dipole like this that is positive or negative, anything or positive or negative. So the angle formed is 90 degree. When angle form is 90 degrees, so the work done at a 90 degree is zero. So finally, the potential energy at a 90 degree is zero. That's why our reference point from where we should rotate, that is electrostatic potential energy of a dipole in a uniform electric field, is defined as work done in rotating a dipole from direction perpendicular to the field, the given direction. See, direction perpendicular to the field. See, let us consider this is an electric field and this is a dipole. Now, if you dwell, the work done here, the condition is zero. Work done is here zero. So from here, either of the direction, if you are moving by angle theta, then only we are taking a reference from here. So if we are taking reference from initial condition from 90 degree to theta, so always take a reference point this as an angle. We don't take this angle. So always take angle from this side. For example, this is a reference line. So your dipole is in this direction. So this will be the angle theta, not this won't be the theta. So here you have to put here. Let us consider we have rotated from uh, this reference line to angle theta, that is this theta. The initial angle was 90 degree and the final angle become theta. So the final angle, there is theta 2. See here, uh, we have used theta 2 minus theta cos theta 1. So in place of theta 2, that is final position is theta and initial position is 90 degree. Right? But the thing is that no. One thing I need to make you understand that don't take this angle from this reference line. You have to take here only. Why it is so? Because see, initial condition was taken from here. So the final condition will be also taken from here. So finally, your derivation will become minus p cos theta. See, your derivation become minus p cos theta. So potential energy is equal to minus p dot e. So this is very important. Okay. Now this is very important. In this case, see here. In this case, the angle is how much? See here, angle of the dipole making with the electric field, that is theta is equal to 0. So if theta is equal to 0, so torque will be 0. So U will be minimum. That is PE. And this is the case of a stable equilibrium. Now, if you rotate it in this direction, so how much potential energy will be there? So theta will be 90 degree. So torque will be maximum torque, that is P cos theta. But potential energy is 0. Why so? Because potential energy is equal to, what is the formula for the potential energy? P dot E. So the potential energy is equal to P dot E. So the dipole moment and electric field angle is how much? 90 degree. So if it is 90 degree, so P, it is dot product, so PE cos 90 degree, so this will become 0, right? Now next was third case. Third case is when you have made a dipole just opposite to this, that is the angle. See the dipole, earlier direction is very important. See, Direction is very important here. See, the direction is very important. See, the dipole moment direction is in this direction and electric field is in this direction. So the theta is here 0. Now the dipole direction is in this direction and the electric field direction is in this direction. So theta will become 90 degree. You need to remember that the dipole direction is from negative to positive. Always try to remember this, right? Now next one is your, see here. So since dipole direction is negative to positive, so here the dipole direction is this direction, but the electric field direction is this direction. So what is the angle? So the angle is 180 degree. So this will be maximum potential energy. So if you want to find the maximum potential energy, so the dipole should be placed in this direction. But this is your unstable equilibrium condition. So try to remember this, very important. So this three question has been asked in a previous year previous year CBSE many times, and it may happen that this year also they will ask you. So try to memorize this. They will. This is the favorite, one of the favorite question of the examiner, right? Now this is the another topic, that is equipotential surface. Equipotential means equal potential. A surface on which the electric potential is same at every point is called equipotential surface. For example, let us consider this is a surface. Potential at this point, at this point, at this point, at this point, everywhere the potential will be suppose 10 volt. It means that this surface is equipotential surface. So now the properties of the equipotential surface, which is very important. No work is done in moving a charge from one potence point to another or equipotential. So why so? See here. Let us consider the potential is. Let us consider. Let us consider at one end. At one end point, the potential is 8 volt, and this end the potential is 6 volt. So what we, if you want to move any charge from 6 volt to 8 volt, so you have to do work, right? You have to do work. But if this will be also 8 volts, so no work is done. Okay, there is no friction. You know that here there will be no friction, so no work will be done when there is a no potential difference, right? So here no work is done in moving, no work is done moving a test charge from one point to another on equitable potential surface. So on equitable potential surface, V will remain constant. Potential difference is equal to 0, no changes in a potential. Second property is the equipotential surface through a point is normal to the electric field at that point. What do you mean by this? See, let us consider this is the surface, equipotential surface. So the electric field will always be at a 90 degree to this surface. If surface may be like curve, so if your surface is curved like this, so let us consider this is the surface. This is the surface. So the angle between the electric field and the surface is 90 always. Now you may be wondering here, you may be wondering that uh, you may be wondering that why this is happening, how you are finding a angle. Let us consider any surface. This is a surface area. You should always remember that the area vector, I have already told this in the previous section. The area vector is always perpendicular to the surface area, right? And the electric field is also perpendicular to this area. So the angle between area vector and electric field will be always 0. So the equipotential surface through a point is normal to the electric field at that point, right? So I hope you have understood now. Okay. So equipotential surface through a point is normal to the electric field at that point. Now let us go for third one. For a uniform electric field, equipotential surfaces are equally spaced. Let us assume that the electric field is uniform. If it is uniform, so the equipotential surface, so this is equipotential surface APS. So APS are is equally spaced. For example, 2 centimeter, here also 2 centimeter. But spaced parallel planes perpendicular to the field. But if it is your non-uniform field, then there will be no equal space. Suppose this is your 4 centimeter, so this will be 3 centimeter, this will be 2 centimeter. So it is unequally spaced placed potential surface. And the one thing you have seen that what you have seen that the distance is also decreasing as we go here. Now, fourth one is your in a region where electric field is strong, equipotential surfaces are close together, and where E is weaker, equipotential surfaces are other. See here in that diagram, I think I have done that mistake of drawing. So let us draw for you. Here I will draw the same thing. See, let us consider this is a electric field, but we can't consider this as electric field. It is your uniform electric field. It is your non-uniform electric field, and this is this side there is a source. So what will happen in this direction? Electric field is decreasing electric field. So that consider when you consider any equipotential surface, when you consider equipotential surface, so how you will draw this? Let us consider there is an like this, equipotential surface like this, another equipotential surface, the gap, try to understand here, the gap is this one, this is your gap. Again, see here, when the electric field is getting decreased, or the strength of electric field is getting decreased, so the gap become more. So let us consider that gap was, let's consider, see here another equipotential surface I can make here. The gap is 1 centimeter, the gap is 2 centimeter, the gap is 4 centimeter. As soon as the gap is increasing, you can consider that that is your weak electric field strength. I hope you have understood now. Total clear. Okay. I hope, is there any problem? I don't think so. So let us go for next step. Now the for point charge equipotential surface are concentric circle. See here, point charge. So this is the point charge. So the circle, concentric circles are the equipotential surface. See this circle everywhere in this sphere there will be equal potential. So no work will be done when the charge is moving on this sphere, charge is moving on this sphere, charge is moving on this sphere, or charge is moving. Okay. Now for an electric dipole, see here, electric dipole, the electric dipole means what? If there is an electric dipole, so what will happen if separately this is positive and this is negative? So what will, it will also create a concentric circle, but it is dipole. So what will happen? If the strengths are strong, so what will happen? We have already discussed, the surface are more near. But as soon as strength become weaker, the surface gap, equipotential surface gap is increasing, right? See here, increasing. See here, increasing. As soon as the gap is, as soon as the strength is decreasing, so the gap between the equipotential surface is increasing. Same thing happens here also. Hope you have understood now, right? Now, for two identical positive charge, so what will happen? So, nothing, there will be a concentric circle only, but there will be a more nearby space here, and at outer end, it will make the because at outer end or at a far distance, they will consider this both as a unit single charge entity. They won't consider a multiple charge. 6 point. Equipotential surface never intersect each other. So this is very important. Equipotential surface, you won't see that the surface is intersecting. No. Okay. Very important thing. The relation between electric field and electric potential. Electric field. The magnitude of the electric field is given by the change in a magnitude of a potential per unit displacement normal to the equipotential surface at that point. What do you mean by this? See here. Let us consider this is a charge Q. Let us consider this is a charge Q. There is an equipotential surface. There is another equipotential surface like this. There will be several equipotential surface, and there is an electric field which is perpendicular to the electrical surface. Now what happens? Electric field E is equal to potential gradient. It means that as soon as electric field intensity will decrease, so the potential will also decrease, and they will decrease in such a way that it will keep this relation. This entity is known as potential gradient. So we will use this in many of the derivation also. So we can also write like this E into dr, right? And this is negative term. So as soon as the electric field is decreasing, so what will happen? Potential gradient, that is potential, will be also decrease. So with the increase in the distance from the source of the electric field, what will happen? There will be decrease in the potential. Here the negative sign indicates that the direction of the electric potential field, potential decreases. So in the direction of electric field, the potential dB is decreases. That's why the negative sign is there. Negative sign is there when you go in the direction of electric field. So what will happen? Potential will be decrease. So this is very important relation. I hope you will be able to remember this, because I will use these things in the upcoming derivation. Okay. Now the important point: potential is a scalar quantity, but the gradient is a quantity. See, in fact, we have already done that. That is equal to 1 by pi. Epsilon not in Q by R. It is a scalar. But the thing is that when we talk about the gradient, so gradient means what? We are relating potential with the displacement. So let us consider this is the potential surface. This is another potential surface like this, right? So when you go, so you are providing a specific direction like this. Means that the potential and direction both are related. That's why when we talk about the gradient, so is your vector quantity. Remember, dV by dr is your vector quantity. Vector quantity, very important. So these are the points you should remember while writing or preparing for the board exam of the 12. Now the direction of electric field is far from high potential to low potential. Definitely high potential to low potential. That is, if there is a positive charge, so what will happen? The direction will be in the direction, the direction of electric field. But if it is your negative charge, so what will happen? The electric field direction will be in backside. So that's why direction of electric field is from high potential to low potential, right? Now, in case of a Cartesian coordinate system, electric field is equal to Ex by Ey z. See, as we know that when we talk about the electric field in x direction, this is the x direction. So this is x. When we talk about the electric field in y direction, so we can directly put here y, Ey. When we talk about the z direction, so we can directly put here z. But the thing is that when we talk about the electric field which is in a space, so how you will define this electric field? So you need three coordinate system, as you have already studied in class 11. So we have already done lots of things in a coordinate system. So this is x, y and z axis. And if we are talking about electric field which are in a space, so what will happen to indicate this electric field? We have to use x-axis, y-axis and z-axis. So here we are using x, y and z-axis. So finally net electric field can be written in the Cartesian form as ex I cap plus ey j cap plus ez k cap. Okay, so I hope you have understood this point. Now ex can also be written like that velocity sorry, potential gradient. See, potential gradient means dv by dr. So r is the distance, so always took like this, take like this. So when the y and z plane are taken, so electric field in x direction, see here, this is y and z direction, so this is x direction. So what will happen? The potential gradient dv by dx is increasing. So this is ex. So ey can be written as potential del v by del y. So these are the higher things we can also discuss later. No need to discuss because it is not in a syllabus. So but till now whatever I have explained, most of the things has been covered, right? Now, one important thing why I'm telling you that you should remember this, because I will use in derivation in further. By formula E minus dV by dx, potential difference between any two points in an electric field is given as dV is equal to minus E dot dr, or delta V is equal to integration E dr. If at any point E is equal to 0, then V is a constant, right? Because E is equal to dV by dr, so E will be 0 means what? E will be constant. Now let us consider there is a charge 8 volt, there is also charge plus 8 volt. So there is no direction of electric field. Why? There will be no use of finding electric field here. See here, this is 8 volt, this is also 8 volt. So from which side there will be no movement of electric field. So when there is a V is constant, so no electric field is there. Okay. So I hope you have understood this. Now one more important thing is from dv by, is equal to dr, so can be written like this, edr dot dr, so this is cos theta. So minus dv by dr can also be written as e cos theta. So minus dv by dr gives the component of electric field in the direction of the dr. See here, this is electric field, this is dr, so you can use like this as well as. Okay, case 1, if dr is in the direction of e theta is 0, and hence dv by dr will be equal to E, that is maximum electric field. So the electric field along the direction in which the potential decreases at the maximum rate. See, this is the surface, this is the direction of electric field. Okay, okay. Now I will tell you, or I will ask you, that in which direction there is a maximum rate of decreasing of potential, in this direction, x direction, or at y direction. At y direction potential will be decrease maximum. Why so? Because see, this is the surface, at least you can see here. Let us make one another surface here. I will make a line like this. See, now if the distance moved here at perpendicularly 90 degrees x, so same length when you move in another direction like this x, so the finally perpendicular distance is less. So it means that the rate of decrease in the movement when you move in this certain angle, so the rate of decrement of the potential is less. But when it is at a 90 degree, so it is faster. See here, it is faster. So the electric field is along the direction in which the potential decreases at the maximum rate is in 90 degree, right? As theta, when theta is in the direction of electric field, right? So if dr is, sorry, not 90 degree, it is 0 degree. Why 0 degree? See here, electric field direction and uh, displacement direction, that is r vector. So both have theta is equal to 0. So when theta is equal to 0, it means that there is a maximum electric field. So I hope you have understood this concept. So if you have any doubt, please join me. Please comment so that I can more explain you more. See case 2, if theta is equal to 90 degree and if theta is equal to 0 degree, so that dv is equal to this for 90 degree case. So v will be constant. For 90 degree it is 0 degree. When it is 0 degree, 0 degree means what? When uh, your movement is in this direction, so there will be constant potential area, right? So this is what we have now done till now. So I hope you have done lots of topics. So we will further discuss in the next video. So be continue and subscribe the channel so that I can give you the maximum potential from my side, so that you can learn the class 12 in a better way. Thank you for joining us.